Welcome back. Today we will discuss characteristic functions. So, if x is a random variable, then the characteristic function is defined as follows. Cx of t is defined as expectation of e power I t x, okay, where t is some real number. Okay. So, this t is some real parameter, x is your random variable. This e power I is of course your I squared is minus 1, right, it is your square root of your minus 1. E power I t x is a complex valued random variable, right. So, which is something again we have not really talked about. So, you can actually take this as expectation of cos t x plus I times expectation of sin t x. Cos t x and sin t x are random variables parameterized by t, and you take their expectations. So, expectation of cos t x plus I times expectation of sin t x. Now, this you know what it means, right, because these are all real valued random variables. So, that is the definition of a characteristic function. Okay. So, this is again defined for any random variable, right. So, for any random variable with probability law p x. So, p x is your law, then C x of t is nothing but integral e power I t little x d p x, right. So, given your probability law you can compute the characteristic function. Again here e power I t x is just cos t x plus I sin t x. So, you can evaluate the real and imaginary part as usual. Okay. So, now this, so why do you need this characteristic function? See, this characteristic function is analogous to a Fourier transform, just like your moment generating function is analogous to a Laplace transform. In particular, when you have a density, if x is a continuous random variable with probability density function f x, then C x of t is equal to integral e power I t x f x of x t x. X is from minus infinity to infinity. Because in the case of a continuous random variable, you know that Radon-Nikodym theorem tells you that dpx is f x dx, right. Yeah, so this is like a Fourier transform of the PDF, except that Fourier transform usually has a negative sign here, it is the only difference. Okay. So, now why do you need this? So, why not just the moment generating function? So, the reason is, so the main reason is that the moment generating function does not always exist outside s is equal to 0, right. As s is equal to 0, moment generating function is equal to 1, but as we saw in the case of a Cauchy random variable, for example, the moment generating function was undefined for all other arguments. But on the other hand, the characteristic function is always well defined and it is finite, okay, for any random variable. So, the reason that is true is the following. So, if you look at so if you, it is true more generally, but if you just look at this for a continuous random variable, if you take absolute value, the absolute value of this integral, then you can bound it above by the integral of the absolute value, right. But the absolute value of e power I t x is 1. So, you will have, so the absolute value of C x of t is upper bounded by 1 always, right. So, so this integral in particular you can show is uniformly convergent for all t, right, for all real t this is uniformly convergent, okay. Absolutely convergent, therefore uniformly convergent. So, this is always well defined, that is one thing. So, you can handle even random variables such as Cauchy. So, you can basically handle these heavy tailed random variables which decay slower than all these exponentials like Cauchy and so on, for which the moment generating function is not defined outside s is equal to 0, but characteristic function will be defined. Okay. The other reason is that at some level this the inversion of characteristic function is a little bit easier than inversion of moment generating function, for the simple reason that just like the inversion of Fourier transform is a little bit easier, right. You can write down an explicit formula which does not involve some very complicated contour integrals over the complex plane and so on, right. So, it is a little bit easier. So, in the case of moment generating function you have to do some pattern matching. Here you can actually write down some more elementary formula for the inversion, that is a more practical reason. So, there is one thing I want to point out. So, let me just give an example, right. So, I think my point will be clear. If I give you an example of, let us say x is exponential with parameter mu, right. So, f x is mu e power minus mu x for x greater than or equal to 0. So, you are used to computing Fourier transforms in your signals and systems. So, you would expect the characteristic function to be the same thing, except that in your Fourier transform you have to be careful about the minus. So, wherever you have a minus in the Fourier transform you have to get rid of that minus essentially, right. So, if you have, so if you in whatever answers you know for your Fourier transforms replace your argument with minus t, right, then you should get your characteristic function. So, just as yes, that is true, right, but I want to make some cautionary remarks. So, I have to give you some caveats here. So, in particular, so if you try to, if you write this, so here is my PDF and my characteristic function will be integral 0 to infinity mu e power minus mu x e power I t x dx, right. Fine. So, now, so this is, I mean again this is an integral you would have computed in signals and systems. So, what you would normally do in signals and systems is that you would just write this as e power minus mu minus I t times x, right. So, you will write this as e power 0 to infinity mu e power minus mu minus I t times x dx, correct, and then you will just, and then the answer is therefore mu over mu minus I t, right. This is for t in R, valid for all real t. So, essentially in going from here to here, what you are basically treating is this mu minus I t you are treating as some a, some real a, right, and then you are just writing this integral down pretending that mu minus I t is some real number, whereas it is not a real number, right, it is in fact a complex number, right. So, in this particular case, I mean, and you would have similarly for the case of in your signals and systems you will get a plus here, that is all, right. The Fourier transform of this exponential curve is a you will have a plus here, that is the only difference, right. Now, this step is not really correct. It so happens that by sheer luck you get this answer if you just pretend that this is a real number, okay. So, what you really have is a function of a complex variable, right, and this integral should be treated as the integral over the contour of the real line, okay. So, in order to evaluate this integral, strictly speaking you have to perform contour integration, right. So, in fact the Fourier transform that you have been evaluating in signals and systems is in fact strictly speaking a contour integral, okay. You see what I mean? So, this is something you do in signals and systems, right, when you compute Fourier transforms. This is not really justified. It so happens that in this case you get the correct answer, even if you perform the contour integration correctly, you get this answer. Okay. It so happens that if you treat this as a real number, you happen to get the right answer by luck. Okay. There are examples where you will not get the correct answer. Okay, if you just pretend that mu minus I t is a real number. So, let me now that I am talking about that, let me just give you I told you the example of a Cauchy, right. So, one of the nice things about the characteristic function is it can help you handle things like the Cauchy distribution, which the moment generating function does not allow you to handle, right. So, if you have a Cauchy, so if you have the Cauchy f x of x is 1 over pi 1 over 1 plus x square, right. So, in this case your C x of t is equal to integral minus infinity e power I t x over pi times 1 plus x squared dx. Okay. So, now in this case actually you cannot pretend this I t is some real number and do this integral, okay, and you will not get the answer. Okay. In fact, you might have done the you have what you have after all is a function that looks like 1 over 1 plus x squared, right, and you have computed its its Fourier transform, right. I mean, do you know its Fourier transform, what it looks like, the functional form e power. So let us go back to, so you think from your signals and systems that the transform should look like e power minus some constant times absolute value of t, right. So, let us just go back to Fourier transforms from your signals and systems for a little bit. So, if you have what do you use x, so f of x, so f of x and f of t for Fourier transform, this is your function, this is your transform, right. So, you have you write down relations like this, right. So, if you have e power minus a x x greater than or equal to 0, the transform, the Fourier transform is like 1 over a plus I t, right, and so and you have e power minus a absolute x, right. You have to help me with this. So, this transforms to what? So, something 2a, right, 2a over a square plus right. See, you know these by heart, right. So, good. So, now what do you do? So this transform you compute this explicitly, again in computing this you will pretend that I t is a real number and add this up, and then you get this answer, right. Then you will invoke Fourier duality, right, to say that if you have something like 1 over 1 plus x squared here, right, you should have something like e power minus absolute t. I am missing some constants, okay. I am surely missing some constants here, but I do not really care about it. I am just saying that if you are given a function that looks like the transform, you use duality and say then the transform should look like this, right, that is what you do, right. So, why do you not integrate this function pretending that e power I t x is a. So, you see what I am saying, right, you never calculate the Fourier transform of this by integration, you always invoke Fourier duality, right. So, the reason is, so in signals and systems you explicitly calculate the transform by integrating in precisely those cases where you can get away by pretending that I t is a real number, okay. In cases like this where you cannot get away by pretending that I t is a real number, you are told that do not integrate, just use Fourier duality or some other property to get the answer. Now, the fact of the matter is, in all these cases just blindly integrating this as a pretending this I t to be a real number is actually wrong. Some cases it gives you the right answer, some cases it does not, okay. So, this is something I want to point out, okay. Actually doing this is possible, okay, but you need contour integration. Okay, so that is not something I will expect of you. I would just want to mention that these integrals are not, I mean you are no longer an undergraduate studying signals and systems. So, I think you should at least know that there is more to it than what you studied in signals and systems. So, if you have something like this, so you have a function that has 1 over 1 plus x squared, right. So, you have to essentially use contour integration and then invoke the residue theorem. Okay. You might have studied the residue theorem in complex analysis. So, what you do in evaluating something like this is that, so this guy has 2 poles, right. This 1 over 1 plus x square has 2 poles, you have a pole at I, you have a pole at minus I, right. So, you are basically integrating like that, right, over this line. So, you approximate, so you what you do is you perform contour integration over a big contour like that, and then you compute that integral using the residue 2 pi I times the residue at I, and then you similarly do it for this pole, and then you have to argue that that integral and that integral will be 0, right, and finally you will get some answer, right, and in fact you will get the answer you expect. I think you will get e power minus absolute t. Okay, you have to do it separately for t greater than 0 and t less than 0, and you will get this answer. Okay. Yeah, so you have to, even here you have to do contour integration, right, but it so happens that you get this answer, which you can, with this you can believe this is harder to believe for you, right, that is because you can no longer treat e power I t as a real number. So, is my point clear? So, even in Fourier transforms this is how you should do it, okay, strictly speaking. Even when you are finding the Fourier transform of this exponential function, you have to actually do contour integration. Okay. So, normally what you do in signal systems is you pretend that this is real, but you only do that in cases where you can get away, and in cases where you can't get away you use some other trick, right. Yeah, I am just pointing that out. Okay. Actually, yeah, so this is a very useful transform to know. Okay, for a Cauchy, e power minus absolute t is the characteristic function. Any questions so far? See, in cases where the moment generating function exists in an interval, you can actually obtain the characteristic function by simply putting s is equal to I t. Okay. So, when the moment generating function exists in some interval around the origin, you know that the moment generating function is an analytic function, and therefore, it is in fact analytic on the imaginary axis as well. So, in those cases you can suppose in this case, right, so you can just put I t, s is equal to I t, even in the case of, let us say in the case of the Gaussian, right, you can blindly put s is equal to I t to get the characteristic function. So, let me just state that, let me just state some elementary properties. So, elementary properties. If y equal to a x plus b, c y of t is equal to e power I b t c x of a t. Okay, this is again from definition. Yeah, so if you have independent random variables x and y and z is equal to x plus y, the characteristic function of z is given by the product of the two characteristic functions. Okay. This is similar to the property for moment generating functions, except you have an advantage. What is the advantage? It exists, right. So, if I mean the same thing is true for moment generating function, but if you are dealing with let us say two Cauchy random variables, the moment generating function will not exist, right. So, if you want to figure out if x and y are Cauchy distributed, IID Cauchy distributed for example like that, if you want to figure out what the sum is like, right, you cannot use moment generating function, but you can use characteristic functions, right. So, in particular you can do this example for yourself. If x and y are independent and identically distributed according to the Cauchy distribution, you know its characteristic function. So, if z is equal to the sum of two standard Cauchy distributions, its characteristic function will be e power minus twice absolute t, correct. So, you would imagine that, so if you invert that characteristic function, you would imagine that you will get another what kind of a, so it will be another Cauchy distribution with a different parameter, right. So, what I am saying is that you will multiply this characteristic function of x and the characteristic function of y is the same thing, right. So, the characteristic function of z will be e power minus twice absolute value of t, right, which looks of the same functional form, right, it looks like e power minus a absolute t, and therefore, z must also be a Cauchy distribution with parameter square root of 2, right, correct. So, using characteristic functions you can figure out that sum of two independent Cauchys is also a Cauchy, which you cannot figure out using moment generating function. So, the proof of this is straightforward by the way, right, it is just from this is just expectation of e power I t z, right. So, z is equal to x plus y, and then this proof is exactly similar to the proof for the moment generating function. So, now you know a new result, you know that sum of two independent Gaussians is a Gaussian, now you also know that sum of two independent Cauchy distributions is a Cauchy distribution, and you cannot figure that out using moment generating function, you have to use characteristic functions, correct. So, this Cauchy is also a stable distribution, so called stable distribution, you keep adding independent Cauchys, you keep getting other Cauchy distributions, okay, just like for the case of the Gaussian which we know, right. For the Gaussian case you can use characteristic function or moment generating function because they both exist, no problem. So, these two are elementary properties. What else? So, you have okay. So, this is not an elementary property, but I will state it without a proof. So, if mx of s less than infinity for s in minus epsilon epsilon, then C x of t equal to m x of I t. This is just what I mentioned earlier, right. If you have, see, if your moment generating function is only defined at the origin, then bad luck, you cannot really, I mean it may be a very, I mean it may not say much about the density, but if you have the moment generating function defined in a neighborhood of the origin, then you know that some very nice properties kick in, right. The moment generating function is analytic, so it gets defined in the entire complex plane, and in particular it will be analytic on the j omega axis or the j I whatever axis you call it, vertical axis, right. So, you can just substitute s is equal to I t and you can get the characteristic function. Okay. So, if you have x is normal 0 1, we know m x of s equal to e power s squared over 2, right, and this is true for all s in the complex plane, right. So, C x of t will be equal to m x of I t, which will be equal to e power minus t squared over 2 for all t belonging to R. Okay. So, the characteristic function of a standard Gaussian is e power minus t squared over 2, right. So, it also looks like a standard Gaussian, right, it looks like e power minus except for the 1 over square root of 2 pi, right. Yeah. So, and then you invoke, suppose you invoke this property, right, then you can figure out the characteristic function of, say, let us say if y is equal to sigma x plus mu, right, then y will become normal mu sigma squared, right. In that case your characteristic function C y of t will be equal to, you apply that rule, right, it will, you will get e power I mu t times C x of a t, which will be e power minus sigma squared t squared over 2. Okay. I am just using this rule. So, that gives you the characteristic function of even non standard Gaussians, mean, mu, variance, sigma squared. So, now that you know this, if you have two independent Gaussians y 1 and y 2 with parameters mu 1 sigma 1 mu 2 sigma 2, you can show that z, which is the sum of the two, will also be Gaussian with the parameters mu is adding up and the sigma squared is adding up, right. So, you can get it from here, but this result you can get it using even moment generating function, right, whereas in the Cauchy case you had to use the characteristic function, right, because the moment generating function does not exist. Is this clear? Yeah, so this is I guess not particularly elementary, but we will not prove this. Okay. Inversion theorem. So, this is just like the inverse of Fourier transform. Okay. So, it is a highly non trivial theorem, by the way. I will just state the inversion theorem for characteristic functions. If two random variables have the same characteristic function, then their CDFs are equal, are the same. So, without proof. further, if x is a continuous random variable, then the PDF can be recovered from the characteristic function as follows. So, I believe this holds only for every x where I believe it holds for every x where f x is continuous. So, if you have, so this is like the Fourier transform inversion, right, except so I guess for the Fourier transform inversion again you are used to writing integral minus infinity to infinity. It is not quite the same as saying the limit t tending to infinity minus t to t, that is because I mean if you write minus infinity to infinity, these two limits can go at different rates, right. So, but this is the correct statement. Okay. So, you have limit t tending to infinity 1 by 2 pi integral minus t to t e power minus I t x c x of t dt. So, this holds, so this holds where f x is continuous. Okay. And if I remember correctly, so this I do not exactly remember, I believe that if your f x is not continuous, if f x has a jump, then this inverse transform converges to the middle point of the discontinuity, right. This is again from your Fourier inversion theorem, right. That is something I do not quite completely remember correctly, but this holds for points of continuity. If you have discontinuity, the inverse transform converges to the middle point of the discontinuity. Okay. This is a non trivial result. Okay. So, this just says actually again this is something we will not really use so often, right. You will, it is much easier to usually do pattern matching and figure out what the density is, if at all there is a density, right. But this theorem just says, oh, you know what, given your characteristic function you can obtain your density whenever there is a density. Okay. And in cases when there is no density, there is actually a more general way to recover the CDF. Okay. I do not know if I should state that. Yeah, so let me not state that because I have I do not have that much time. So, the characteristic function is defined even when x is not continuous, and if you are given the characteristic function of a random variable which is not a continuous random variable, you can, there is a way to invert it to obtain the CDF. Okay. Maybe I will put that in the notes. Okay. Let me not spend class time on it. Okay, so this is a very important theorem. So, these I will call these defining properties. Okay. So, you will very soon realize why these properties are defining properties of a characteristic function. If x is a random variable with characteristic function C x of t, then property A C x of 0 equal to 1 and absolute value of C x of t less than or equal to 1 for all t in R. Okay. This is something you will understand very easily, right. C x of 0 is obviously 1, it is expectation of 1, right, if you are putting t equal to 0, and I argued that absolute value of C x of t is less than or equal to 1, correct. I think I did not write it out, but I argued it out. B, C x of t is uniformly continuous on R. i.e., for all t in R, there exists a psi of h, maybe I should call it, this is not the conditional expectation or anything, okay. Maybe I should call it, I call psi for conditional expectation, right. So, maybe I should call it phi of h, okay, phi of h, which goes to 0 as h goes to 0, such that absolute value of C x of t plus h minus C x of t is less than or equal to phi of h. Okay. So, this is the second property. So, this essentially says that characteristic function is a continuous function of t, is actually a uniformly continuous function of t. Uniform continuity is a stronger form of continuity. Okay. Uniform continuity implies continuity, but not the other way around. In particular, uniform continuity is exactly what I have said here. Okay. So, normally you mean by continuity you mean that this absolute difference is small as goes to 0 as h tends to 0, right, that is what you mean by continuity. But in the case of uniform continuity, no matter what t you choose, this absolute difference is uniformly bounded by this function phi of h. See, normally you only need that this difference goes to 0 as h goes to 0, correct, but here you are demanding that no matter what t is, you can choose a phi of h such that this difference is uniformly bounded above by phi of h, and this phi of h is a function that goes to 0 as h goes to 0. Okay, in some sense you are saying that this difference itself does not depend on the value of t, right, it is irrespective of the value of t, it is bounded above by some phi of h, right, that is stronger than a continuous function, right, saying more than continuity, it is called uniform continuity. Okay. C x, the third property is C x is a non negative definite kernel. I.e., for any n and real t1 t2 tn and any complex z1 z2 zn, we have sum over jk zj cx of tj minus T k z k conjugate is greater than or equal to 0. So, this is a property that seems, this is a very fundamental property of characteristic functions. It does look a little bit looks a little bit hard to digest in the beginning, right. I will help you parse this. So, what you are saying is that you are considering these complex quadratic forms, right. This is like complex quadratic form. You are fixing some n, all right, fix any positive integer n, and you pick any real t 1 t 2 t n you want, any complex z 1 z 2 z n you want, okay. And then you are looking at, so let me put this in a matrix form, so that is a little bit easier to digest, right. So, you are looking at a matrix in which the I jth entry is C x of T j minus T k. This is the I jth entry of the matrix or j kth entry of the matrix, okay. And therefore, the diagonal entries will be what? Ones, right, they are all ones, because you will have T j minus T j, which is 0, C x of 0 is 1, right. You will have ones on this main diagonal, all the diagonal, and you will have these kind of terms on the j kth entry, and then you are essentially what you are doing is, so really what you are doing is that you are taking the z's like that, right, or maybe this is z bars, right, these are all z bars, this is z 1 z 2 z n, right. You are looking at a quadratic form of that kind, that is what this is, come to think of it, right. And you are saying that for no matter what these t j's are, no matter what these z i's are, this quadratic form is always, this complex quadratic form is always non negative, okay, fine. So, is it clear what it says? So, I am saying that this is exactly the same as this. So, you arrange you choose your T j's and you form this matrix, right. Then this matrix will have, this matrix is a non negative kernel, in the sense that all complex quadratic forms are non negative, okay. So, we have to prove this results, right. So, this first bit is easy, isn't it? This is quite trivial, this and this needs some work, okay. So, how am I on time? I am probably, I just have like 2-3 minutes, maybe I will just try and do part B. So, it says 5 more minutes. So, let me just do part B, and part C maybe we will do next class, okay. So, I am trying to prove uniform continuity. So, you have absolute value of C x of t plus h minus C x of t is equal to absolute value of e power expectation of e power I t plus h x minus e power I t x, isn't it, right. So, that is equal to, I can write this as absolute value of that, right, I think this is right. Absolute value of expectation of e power I t x times e power I t h minus 1, right, agree with that. H x yeah sorry right correct. Now this will become, so this you can show is less than or equal to expectation of e power I h x minus 1 correct, because this absolute value will be equal to 1. Okay. So, this is what you have to look at, right. So, this is like, so if you look at this is what. So, this will be like the absolute value will be like, so if you write e power I h x as cos h x plus I sin h x, right. So, this will become, so absolute value of e power I h x minus 1 is equal to square root of you can show that this is nothing but square root of 2 minus 2 cos h x, just trigonometric identities. Okay. And then this is equal to 2 times the absolute value of sin h x over 2 correct. So, I am just expanding this cos x. So, just the absolute value of a complex number is is equal to square root of the real part square imaginary part square, simplify sin square plus cos square equal to 1, you do all that, you end up with this. So, essentially what we are saying is that this guy will be less than or equal to 2, is not it. So, this is essentially less than or equal to 2. So, this is my, so okay, so this is my, this is what my phi of h is. Okay. So, I have to prove that my phi of h tends to 0 as h tends to 0, but as my h tends to 0, so I have to use dominated convergence theorem now. So, I can take the limit inside, right. So, it is a bounded, so it is dominated above by 2, right. So, I can take the limit inside and this guy obviously goes to 0, right, as h goes to 0 correct. So, by dominated convergence theorem we will get the result, that is the step I was missing. Okay. So, maybe we will recap this next class. Okay. Stop here.